Why is it that if I take this coin, place it in this bowl of water, it sinks? But if I take this piece of paper, fold it into the shape of a boat, it floats? Moreover, how can we determine how much load this boat can handle before it sinks? Or for submarines, how can we find out if it will actually stay upright when we submerge it in water? These questions, among others, are considered in the study of ship stability. And this video on this channel will be the first video in a series exploring basic concepts of this topic of ship stability. So if you're new to this channel explores all things engineering related. And if that's something you're interested in, consider subscribing. Okay, so this video being the first video in the series, I'll discuss the most basic concepts and then gradually work our way up in complexity. And naturally, this begins with the question of why do things float? It's kind of bizarre that this coin, right, sinks, but this monstrosity of a ship floats. Lucky for us, there was this guy in Greece, Archimedes, who lived in around 200 BC, and he made an observation that we now know today as Archimedes Principle. And this observation states that when an object is immersed or partially immersed in a fluid, it experiences an upward thrust equal to the weight of the fluid that it displaces. The upward thrust is also known as the force of buoyancy. Great, so now we know that when an object is in a fluid, it experiences the force of buoyancy. But obviously, this isn't the only force present, or this coin wouldn't sink. So there must be another force, and it's one that we're all familiar with. It's gravity. It's the interaction of the force of buoyancy and the force of gravity that determines if an object floats or sinks. How do we calculate the force of buoyancy and the force of gravity? Okay, we'll start with the force of buoyancy, and for that, this is just expressed in Archimedes' principle. The force of buoyancy is equal to the weight of the water or fluid displaced. Mathematically, we can express this as being the weight of the fluid is equal to the mass of the fluid times the acceleration due to gravity. The mass of the fluid can be expressed in terms of density and volume, and the acceleration due to gravity is just a constant. It's 9.81 meters per second squared. For the force of gravity, this is just the force of gravity is equal to the mass of the object times the acceleration due to gravity. Because an object that is floating has these forces in equilibrium, we can equate these expressions and then simplify to end up with the mass of the object is equal to the mass of the fluid displaced. And if you've ever wondered, this is how we weigh ships. Practically, this procedure involves reading draft marks on the side of the ship's hull, and then we look up on tables that correlate the draft marks to the weight of the ship. The next term I want to talk about then is this term reserve of buoyancy. Reserve of buoyancy is defined as the volume of the watertight sections above the ship's design waterline. Why is this important? Well, because it represents a safety margin. When you add weight to a ship that's sitting in water, it sits lower in the water. And the watertight sections that were initially above the waterline that now sit below the waterline add to the buoyancy force and stabilize the ship. Now, a term related to the reserve of buoyancy is freeboard. Freeboard is the distance from the ship's design waterline to the highest continuous watertight deck. If we go from the design waterline to the keel, that distance is known as draft. Then there's center of buoyancy. The center of buoyancy is the point on a vessel where all the buoyant forces appear to act. The center of buoyancy is located at the centroid of the submerged volume. And if there's a center of buoyancy, there must also be a center of gravity, and this is the point on a ship where all the weight appears to act. This is determined by the distribution of mass within the object. For instance, in the case of this Sharpie, we can see that there's a greater distribution of mass toward the cap end, So if I were to try to balance it, we can see that that is in fact the case. Continuing on with this theme of centers, there's then the center of flotation. This is a bit of an abstract one to wrap your head around, but if you think about a ship that's sitting in water, the cross section at the water line is known as the water plane area, and the centroid of this cross section is the center of flotation. Why is this of significance? Because it's the point about which the ship trims, and so it's the balance point of trim. And for most ships, this center of flotation is a little aft of midships. And that's because the design of most ships' hull is such that it has a more full of form toward the stern than the bow. The next term then is metacenter. To understand this term, let's consider a scenario where we have our ship being acted upon by an external force, causing it to heel. Now when that ship is upright, the force of buoyancy acts at the center of buoyancy, which, as I had mentioned, is located at the centroid of the underwater volume. When the vessel heels, the underwater volume changes, and so the location of the center of buoyancy also changes. In this scenario, where we have the ship leaning to starboard, that center of buoyancy moves to the low side. But notice that that force of buoyancy is still acting vertically upward. If we extend the line of action of this force, at some point it intersects the center line of the vessel. That point of intersection is known as the metacenter. The distance between the metacenter and the center of gravity is known as the metacentric height. In this scenario, the center of gravity hasn't changed, and that's because the weight distribution of the object hasn't changed. Now the reason why this abstract reference point, the metacenter, is of significance to naval architects is because it represents the ship's stability. And to see that, we have to consider another term, and that is the righting lever. If you compare the ship in its upright position to its heeled position, what you'll see is that in the upright position, the center of buoyancy and the center of gravity are right on top of each other. One's pushing down and one's pushing up. Because the lines of action of these forces are coincident, the ship is in equilibrium. Now, in the heeled position, the center of buoyancy is offset, and because of that, you end up with a righting moment. The righting moment is working to bring the ship back to the upright position. Now, if you draw a line from the center of gravity and you intersect with the line of action of the center of buoyancy, right, you end up with the righting lever. This is commonly abbreviated as GZ. And that line, GZ, is a visual indication of that righting lever. So the larger that line, the larger the magnitude of the righting lever and the larger the magnitude of the righting moment. So for the same angle of heel, if the center of gravity was lower, we could see that we would have a greater righting lever, and so the ship would have greater stability. Now we can use trigonometry to mathematically express the righting lever, and if you recall from basic trigonometry, you have the expression SOHCAHTOA. So to express the angle theta, we can say that sine theta is equal to opposite over hypotenuse, and in that case, we would have sine theta is equal to GZ over GM. Now, isolating for the righting lever, we then have GZ is equal to GM sine theta. I should mention a caveat, and that is that this expression is only valid for small angles of heel, and small angles of heel being defined as 1 to 10 degrees. There are some sources that I've read that say up to 15 degrees, but what you have to understand is that the relationship between the angle of heel and the righting lever is only linear for a small range of angles. After that, it gets more complex and you have to use computer models to determine the righting lever. Now we can extend this formula to also mathematically express the righting moment. The righting moment is a torque, and torque is a force times a distance. So here the force is the force of buoyancy and the distance is GZ. So substituting the displacement of the ship for the force of buoyancy and GM sine theta, we end up with this final expression. One more thing that I want to mention before ending this video is that the writing lever and writing moment isn't always positive. In fact, it keeps increasing for angles of heel up to a certain maximum, and at which point it then begins to decrease and eventually becomes negative. And a negative writing moment isn't working to right the ship, but it's working to capsize the ship. I'll talk more about this when I go into how to plot GZ curves. And so if it isn't fully clicking right now, just hang in there. I'll clarify in the next video. In the next video, I'll also talk about inclining experiments, hydrostatic curves, and GZ curves. So if that's something you're interested in, consider subscribing to be notified when that video comes out. If you have a topic of marine engineering that you'd like me to cover, let me know in the comments below and I'll try and do my best to get to it. Okay, thanks for watching this video and I hope you learned something.